All right. Welcome to lecture, whatever this number is being the title, on implicit differentiation. Okay, so we're going to start off just with a motivating example to sort of get an idea of what this thing is. Okay, so suppose we want to find the tangent line of the ellipse given by x squared plus 3xy plus y squared equals 25. All right, so let's remind ourselves that an ellipse is like an oval sort of shape. And we're looking for the equation of the tangent line really just at any arbitrary point. So let's just pick this point out here. Looking for an equation of this tangent line here. Okay, so what do we need to do? Well, typically to find a tangent line, you need a slope and a point. Well, all right, we could pick a point, but more importantly, we need a slope. So to find slope, we need a derivative. Now, this is expressed in sort of a strange way, right? I don't have f of x equals something. I don't have y equals something. I have x and y sort of intertwined here, right? So in order to find the derivative, I need to write y equals something, meaning I need to solve for y. And when I solve for y, I get the following, just by using the quadratic formula. And this, of course, is horrifying. Awful. And most importantly, yucky. So what do we do instead? Alternative, use implicit differentiation. Right? And I'm going to underline implicit. Right? Over here, we've found an explicit expression for y, and then we can take a derivative. We can definitely find the derivative of each of these, right? The plus and the minus part. But it's easier if we just look at y as y of x, or f of x. So what do I mean by that? Let's return to the original function, x squared plus 3xy plus y squared equals 25. And let's rewrite as x squared plus 3x y of x plus y of x squared equals 25. Okay, so I can write this because, as we've just seen in the previous slide, that y is really a function of x. Y equals that big jumbled mess only involving x. So y is a function of x. Give me an input of x, and I get an output of y. X is the independent variable, y is the dependent variable. So I can just sort of reckon this y, as a function of x, and that's exactly what I'm doing. So now without solving it for y, I can still find the derivative of y. And how do I do it? Well, take the derivative with respect to x of both sides and apply chain rule. So what do I mean by that? Well, I'll take a derivative of both sides. Okay. Distributing this through, I get derivative of x squared plus derivative with respect to x of 3x y of x plus the derivative with respect to x of y of x squared equals derivative of 25 is just 0, right? Because this is just a constant. Now, notice these are regular old real life d's. They're not the scripty d's. I'm not taking a partial derivative here. I'm taking the derivative with respect to x. This part right here is crucial, right? It's important now in this that I'm taking a derivative with respect to x. So I'm gonna move away from using that prime notation. Rather than writing y prime, I'm gonna use dy dx because it's important what the independent variable is. So we're gonna avoid this and use this instead, okay? All right, so how do I do this? Well, this part's easy. This is just 2x. Now taking the derivative here, I have 3x over here, and I also have that multiplied by y of x. This is a function of x, and how I think of y of x is just a set of parentheses with some x's living in the middle of them. So how do I take a derivative? Well, I say I have a product rule, so I'm going to have the derivative of the first times the second. Great, we'll put this in brackets just to see where everything is coming from, plus the first times the derivative of the second. And what's the derivative of y with respect to x? Well, it's exactly that, the derivative of y with respect to x. And you could even write, alternatively, y prime of x. The prime notation is okay so long as you keep the x involved. As long as you keep this x here, this sort of substitutes for this bottom part here. Right? Okay, so that takes care of that derivative, right? Derivative of the first times the second plus first times the derivative of the second. Plus, now I have this. This is where the chain rule comes in. The derivative of y with respect to x squared is the derivative of a function squared. So what do I do to this? I do chain rule. I bring the 2 down and I keep the function the same. And then I multiply by the derivative of the function, right? Of the inside. I've applied power rule to the big set of parentheses, bring the 2 down, drop the power to 1, multiply by the derivative of the inside. This is just an application of chain rule. And I still have 0 on the right-hand side. Okay, moving up here, what do I get? I get, just simplifying out a little bit, making it look a little nicer. I get this. This is just me rewriting and getting rid of those brackets and parentheses and stuff. Okay, so here's what I have. Well, now what? Remember, we're looking for the derivative of y with respect to x, right? Back here, I would have taken the derivative of both sides, and I would have gotten y prime, right? Or dy dx. And over here, I would have gotten what I was looking for. So dy dx is really the thing that we're looking for here, right? So I have to treat dy dx as any other symbol and use algebra to solve for it. All right, so I will copy down what I have. I should use y of x here. Dx equals 0. Okay, so I want to solve for dy dx. I have two instances of it. This is something I can handle. Let's isolate any term with a dy dx in it, right? Just as we would isolate any term with an x in it, or whatever we were choosing to solve for. So I get 3x dy dx plus 2y of x dy dx equals negative 2x minus 3y of x. And you can drop the of x. I'm just doing this just to emphasize that y is a function of x. But if you understand that, then you're more than welcome to just write y. And I'll probably start doing that at some point just to save room. Okay, so I have my dy dx's on the same side. That means I can factor them out. Oh, sorry. Factor them out. 3x plus 2y of x still equal to this. And then divide. This is as if I was saying 5 times this, right? This is just some number that I want to get rid of, right? To get rid of this attachment, I have to divide both sides by 3x plus 2y. So I have negative 2x minus 3y of x over 3x plus 2y of x. And this is my derivative. Now I've taken my derivative and I know what it is without ever having to solve for y. That's why it's called implicit differentiation. I never knew what y of x explicitly was. And I didn't need to. And that's sort of the beauty of implicit differentiation. Okay, so I would say that is the chain rule method of implicit differentiation. Now, we have the benefit of seeing partial derivatives already. Probably poor grammar, but fine. My point being, we've seen partial derivatives already. This is usually not the case in, say, Math 21 or 75 or 51 or any of the other things, because partial derivatives are typically a calculus 3 thing. However, because we've seen them, our life becomes easier. So there is a chain rule method shown in motivating example. And there is the partial derivative method. And this is just a formula you can memorize. So if a function in two variables f of x, y is equal to a constant c, then dy dx is equal to the negative of the partial of f with respect to x over the partial of f with respect to y. Okay? This, written in different notation, is negative f sub x over f sub y. And this is, the way I remember it is, it's exactly the opposite of what I have on the left. What I have on the left is a regular d. What I have on the right are scripty d's, meaning partials. What I have on the left is y on top, x on bottom. What I have on the right is x on top, y on bottom. What's on the left is positive, what's on the right is negative. It's exactly the opposite in every sense of the word. Okay? Now, this is much easier than the chain rule method. The chain rule method is sort of the standard way that these are shown, but like I said, we have the extra power of having partial derivatives. Okay, so let's take a look at an example where we use these, and in fact, it'll be the same example we just looked at. So I'll even say returning to motivating example. I have what? X squared plus 3xy plus y squared equals 25. Okay, so first I need to find out, do I have a function in two variables which is equal to a constant? Do I have some big F of x and y equal to c? And in this case, yes, I do. Yes. F of xy is the left-hand side. 3x squared plus 3y plus y squared. And f of xy is equal to 25. Right? F of xy is just this thing here. And it's already to the point where I have a constant on one side. You can always make this the case, even say, for example, say I had x squared equals 3xy negative 3xy minus y squared plus 25. Just solve so that there is a constant on one side. So just bring the negative 3xy and the y squared over to this side. Or you could even do bringing the x squared over to this side, because then I would have 0 on one side, and 0 is certainly a constant. So in either case, I have different f of x, y's, but the answer still comes out exactly the same. So if you're ever uncomfortable, if it's not clear whether it is or not, just make sure that 0 is on one side, and you'll always be safe. But this has to be true in order to apply that shortcut rule. Step 2 is to find the partials. I need to find the partial of big F with respect to x and the partial of big F with respect to y. Okay, with respect to x, I'm just looking at this function here, and I have 2x, 3y plus 3y, and y, that's just treated as a constant when I do a partial derivative, right? This is why it's important to have this scripty d here, because if I was taking a regular straight up and down d, then y is viewed as a function of x, and I'd have to apply a chain rule here. And this would be a product rule, right? This would be a much different looking problem. But because I'm using these scripty d's, this signifies that I'm taking the partial derivative, meaning anything that isn't an x in this case is a constant. And anything that isn't a y in this case is a constant. So the derivative of x squared with respect to y is 0. Derivative of 3xy with respect to y is 3x, and the derivative of y squared is 2y. And then finally, step 3 is simply apply the rule. I'm looking for dy dx, and these are regular straight up and down d's. This needs to be equal to negative df dx over df dy. I know what these values are. So I get negative 2x plus 3y, and parentheses are recommended, over 3x plus 2y. And you will notice, checking our answer, that we had negative 2x minus 3y over 3x plus 2y. Negative 2x minus 3y over 3x plus 2y. Same thing, this way is a lot shorter. Okay, one final example. We'll be given the function k squared L plus 2e to the k equals kl minus 5 plus L. And the instructions are simply to find dk dl. And that will be part A, and part B will be find the equation of the tangent line at the point 7, 0. Okay, so this, first of all, gives away that k is a function of L. So we may write k of L. Wow, I cannot write a k. K of L. Anywhere we see a k, right? This is sort of the y in the example that we looked at before, and L would be the x. Okay, and I only say that because we're going to be using the chain rule method as well as the partial derivative method, just to show both for the sake of illustrating. Okay, so first we use the partial method. So I need to get this equation to look like something which has a constant on one side. So it looks like I can just bring everything except the 5 over to the left-hand side. So rewrite the given equation. Can't spell either. Equation as k squared L plus 2e to the k minus KL minus L. And this equals -5. Okay? This is in the correct form of f of, in this case now, KL, or I guess to keep it consistent, LK equals a constant. That's good. So now I can apply the shortcut. dk dl is negative df dl over partial f partial k. And we should come off to the side here and figure out what these partials are. Partial of f with respect to L is k squared minus k minus 1. And partial of f with respect to k is 2kl plus 2e to the k minus L. Okay, so it looks like I have, and I'll distribute this negative through, or maybe I'll write it out in 2 steps. K squared minus k minus 1 all over 2kl plus 2e to the k minus L. Make sure I wrote that in the right order. Yes, looks good. Great. All right, so I've answered part A using the partial method. Now, let's try it using the chain rule method, just to see how much worse our life would be. A. Chain rule method. Okay, so I had k squared L, 2e to the k squared L plus 2e to the k equals KL minus 5 plus L. Okay, now I want to take a derivative with respect to L. So I'm going to rewrite as k of L squared times L plus 2e to the k of L equals k of L times L minus 5 plus L. All right, so it looks like here I have a product with a chain rule. Here I have a chain rule. Here I have a product rule. And yeah, this just looks like a power rule, and this is just a constant. Okay, so maybe not too bad. So taking a derivative of both sides with respect to L, I get the following. Taking the derivative of the first times the second plus the derivative of the second, which is just 1, times the first. Great. And I'll write k squared of L here. Plus 2e to the kl times the derivative of the exponent equals, and I have another product rule, derivative of the first times the second plus the first times the derivative of the second, which again is just 1. Derivative of 5 with respect to L is just 0, and the derivative of L is 1. Okay, bringing all of the dk dLs to one side and everything else over to the other. I'm going to start writing k instead of k of L, just to save on space. I get the following. And then I get k plus 1 minus k squared. I've brought this guy over. I've brought this guy over to here, and everything looks good. Great. Okay, so I factor out dk dl. I'm left with 2kl plus 2e to the k minus l equals k plus 1 minus k squared. And I get dk dl is negative k squared plus k plus 1 all over 2kl plus 2e to the k minus l. And let's see if that matches up. 2kl plus 2e to the k minus l on the bottom, and negative k squared plus k plus 1 on the top. And that looks right. So it should be clear at this point that the chain rule method is a lot worse, and you should avoid it at all costs. But should you choose to do this, there is nothing wrong with it. If you like doing algebra and you're confident that you won't make any mistakes, fine, stick with chain rule. But if you're comfortable with partial derivatives in any way, shape, or form, you should use the partial method. Okay, so now all that's left to do is do part B, which is just, I'll remind you, find equation of tangent line at the point 7, 0. Okay, so remember that L is sort of acting as our X here, and K is acting as our output, our Y. So I need to find the slope first, right? I need to find the slope of the line, of the tangent line at that point. So I'll write it as this. This is a notation that maybe you haven't seen yet. But when using the dk over dl notation rather than the prime notation, this is typically how it's written. You'll see derivative, and this bar means evaluated at the point 7, 0. So this just means take a derivative, plug in 7 for L, plug in 0 for K. That's all that means. Okay, so let's return and find out what our derivative was. Negative k squared plus k plus 1. So it's negative 0 squared plus 0 plus 1, just plugging in for k. Remember, k is equal to 0 here. And 2kl plus 2e to the k. 2kl plus 2e to the k minus l, which is 7. Simply evaluating here, I get 0, 0, 1, 1 on the top, and 0 and a 1, 2 times 1 gives me 2, minus 7 is negative 5. So again, negative 1/5 is my slope. So this is my m tan, the slope of my tangent line. I already have a point, 7, 0. So I can find the equation. This is k is now acting as our y, right? Is ml plus b, if we want to write it this way, or probably the better way to write it. Actually, I should probably just stick with point slope form. K minus K1 equals M tan L minus L1. Okay, so just plugging in the appropriate things, I get K. I cannot write a K. K minus K1 is 0 in this case. M tan is negative 1/5. L minus 7. So just simplifying. get this. And that's what we're after. Nothing different here, just different variables floating around. Really, all the heavy lifting took place in finding out what this thing was.